Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Tier, and today I'm going to talk about an important topic. This is related to the Pythagorean theorem, and it's called Pythagorean triples. And what are Pythagorean triples? They're just triples of integers a, b, c, such that a squared plus b squared equals c squared. So, in other words, they're triples of integers that can be the lengths of the sides of a right triangle, where A and B are the lengths of the legs and C is the length of the hypotenuse, but they're all integers. That's what a Pythagorean triple is. And I think you guys know some of them already. 3, 4, 5, that's the most well-known Pythagorean triple. After that, 5, 12, 13, 7, 24, 25, 8, 15, 17. There's infinitely many. You might wonder how we get these. Well, here this slide shows you how to do that. So it turns out the Greeks discovered this. I think it was Euclid who discovered this formula. If you just to pick any two integers, m and n, positive integers, m and n, with m greater than n, then if you let a equals m squared minus n squared, and b equals 2mn, and c equals m squared plus n squared, then it's necessarily true that a squared plus b squared equals c squared. You can do the algebra to check this yourself. I don't want to do it right now, but it's pretty easy to check. It's a nice exercise in algebra. Show that a squared plus b squared equals c squared, where a, b, and c are given by these three formulas. Anyway, the Greeks discovered this. And it turns out that for any integers m and n, this is true. And here's a table. So, like I said, this will generate infinitely many primitive Pythagorean triples. You can see on the in the left two columns you have m and n. Those are just arbitrary integers with m greater than n, so m has to be at least 2, n has to be less than m. So you start with 2 and 1, that gives you the usual 3, 4, 5 right triangle. And then the next one is 3 and 1, that gives you 8, 6, 10. Notice that that one's not what we call a primitive Pythagorean triple, though. What that means is that the A, B, and C are not all relatively prime. In this case, they're all even. It turns out that half of all these pairs M and N give you pairs in which A, B, and C are not coprime because they're all even. The greatest common factor is still 2 in that case, but the other half, the ones where M and N have the opposite parity, it turns out. One is odd and one is even. That's kind of another requirement we need to make in order to make sure that they're primitive. And here's another table. This is a little bit smaller table, but this has the first several primitive Pythagorean triples, A, B, C. In this case, A, B, and C are all relatively prime, or co-prime, if you like. And here they call them I and J instead of M and N. But in this case, I and J, not only is it true that I is always greater than J, but they have opposite parity. One is odd and one is even. And it turns out if you make those two restrictions, that gives you all primitive Pythagorean triples. It's a little harder to prove this gives you all, but it does. I guess I didn't present a proof of that in this video, maybe in another video. But there's actually another way you can get these, which I think is kind of interesting. This is a geometric construction. It turns out that if you start with a circle, a unit circle, so this is a circle of radius 1 in the xy plane, and you take any line passing through the point -1 comma 0. That's the point on that intersects the x-axis at the left. There's 2 points on the circle that intersect the x-axis. One on the left is -1 comma 0. So you make any line through that point, and that line, as long as it's not a vertical line, I guess you don't want a horizontal line either, but as long as you take a line that's not vertical or horizontal, any other line, it turns out, will intersect this circle at a second point. And that point, if the slope, and that slope has to be rational, by the way. So we call the slope t. T is just any rational number. It turns out if you pick any rational number t for the slope of this line, then the intersection point, the second intersection point of the line with this unit circle is the point whose coordinates, the x coordinate is 1 minus t squared over 1 plus t squared, and the y coordinate is 2t over 1 plus t squared. And if you let t equal m over n, or n over m, it'll again give you all the primitive Pythagorean triples. I just think that's a nice thing. That's another way you can get them. You can do a geometric construction to get them. And here's a bigger list. This list, so like I said, not all Pythagorean triples are primitive. If you want to get all of them, all you have to do is multiply the primitive ones by an arbitrary multiple. And this table shows the first several of those. And so they don't only involve m and n. In this case, they also involve a multiplying factor. I don't know what they call this. Might be a little hard to see. But for the third triple they show, I think we have to multiply them both by 2. The next one, it looks like the 6, 9, 12, 15, we have to multiply them all by 3. Turns out you don't get these if you just use m and n. You always get primitive or almost primitive ones. But if you want to get them all, you have to multiply by something else. So anyway, and here's a scatter plot. I think this is kind of an interesting plot. This is a scatter plot of all the primitive Pythagorean triples with sides up to I think 4,500. Kind of an interesting picture, I think. It just shows you how many there are. There's definitely many, like I said, and they fall on this nice kind of scatter plot. I think they're showing m and n here. I'm not even sure what they're showing, but if you pick these particular values of m and n, then you get a primitive Pythagorean triangle. I think that's what that's showing. So there's a lot of them. I mean, and this is I think this is actually the most interesting thing I've ever learned about primitive Pythagorean triples. It turns out there's another way to generate them, and this was discovered fairly recently. These are trees. These are ternary trees. So a ternary tree is just a tree in which every node has exactly 3 branches. So on the left you start with the root of the tree. That's 3, 4, 5, and then you get 3 branches from that tree. And there's a rule for getting there. There's a simple rule involving matrices, 3 by 3 matrices, from getting the next level of this tree from the previous one. And you just multiply 3, 4, 5 by each of the 3 by 3 matrices, and then you get the next level, which it looks like is 5, 12, 13, 21, 20, 29, and 15, 8, 17. That's the next level. You multiply the same matrices again to each of those. You get 3 more on each branch. You're going to get 9 this time on the second level, then 27. This is just the first 3 levels of this tree, and of course this tree can go infinitely far. The guy who discovered this, the mathematician who discovered this tree, was named Berggren. I believe he was Dutch, and he discovered this in 1934. Pretty amazing construction, I think. I would have never thought this was possible, but it turns out that yeah, you can get all the primitive Pythagorean triples from a ternary tree, and not just one. It turns out there was another one. Maybe I didn't put it in here. Oh, yeah, I think I did. There's 2 of them. I guess these slides almost look the same. But there was another one discovered by another mathematician named Price, I think in 1967, about 30 years later. He discovered a different tree, which you can use different matrices to get. Again, you start with 3, 4, 5. This time you get different Pythagorean triples, primitive Pythagorean triples on the first level. This time you get, it looks like 5, 12, 13, 15, 8, 17, and 7, 24, 25. I believe they were different on the previous slide. So this is a different tree. But once again, it gives you the exact same set of primitive Pythagorean triples. Pretty amazing. So anyway, that's my talk on primitive Pythagorean triples. I hope you enjoyed it, and I'll see you next time. And thank you, and long live math.